Hello everyone. This is the video for your 3.1 exponential growth and decay notes. So if you've not already grabbed the 3.1 notes and a copy of the Unit 3 table of contents, please go do that now. And then we're going to fill in some table of contents and some notes today. So we just finished a unit 2. So we're going to start with the very first table of contents in our notebooks, which is the whole Algebra 2 table of contents. So go ahead and fill in over here. Whatever page you ended unit 2, your function transformations on for your 2.6 notes. For me, that was page number 15. Then we're going to add in unit number 3. And unit number 3 is about exponential functions. Exponential functions. So for me, that's going to start on page 16, and I don't know where that's going to take me to yet. Once you have that written, grab that orange table of contents. Let's fill that in at the top. So this is unit number 3. Exponential functions. And our notes today are note number 3.1. It's called exponential growth and decay. For me, this is going to be on page number 17 in my book, in my notebook, since this table of contents will be on page number 16. Once you have done that, let's go to those notes. Go ahead and fold them like we've folded the rest of our notes here. And let's talk about these notes. So we have 3.1, exponential growth and decay. And looking at our learning target here, I can use exponential functions to model real-world phenomena. I'm going to underline exponential functions here. We learned about exponential functions just a little bit. We just were introduced to them in our function transformations unit. If you remember correctly, those were the functions that had a variable in the exponent. That's what made it an exponential function. Now, there's a lot of things in this world, in the real world, that can be modeled with an exponential function. So we're really going to focus this unit and our learning in this unit around using what we're learning about exponential functions to relate it back to the real world. So for example, down below, you will see a quick little graph here that models the data around the world days after March 1st, 2020, with daily new confirmed COVID-19 cases. So if you think back, so this is by day, this is not by year, but you can see that it started out kind of slow and then all of a sudden started shooting up very quickly, right, as we started our international pandemic. And this is the model of the best fitting model here is an exponential model, as you can see from that blue line. So let's take a look at our notes. Go ahead and open those up. And we're going to start with the format of an exponential function. There's kind of two formats here. So we're going to start with our most common first function, or first one, and that is going to be a times b to the x power. A times b to the x power. A is known as the initial or starting value. So it's whatever the starting value for your function or your situation is. If b is greater than 1, we're going to have exponential growth, okay? So the function is going to be getting bigger and bigger and bigger as that x gets bigger. Now, if b is between 0 and 1, we will have exponential decay. So this is like a decrease. If you think of that word decay, I want you to think for a moment, where have you heard the word decay before? Maybe you're thinking of it in terms of the biological form of decay, where, leaves decay after they fall out of the trees, right? That's when they're breaking down, they're breaking apart, they're getting smaller. So it's the similar idea here, where exponential decay is when things are decreasing, and exponential growth is when we are increasing. Now, there's an alternate form that we use mostly with percentages, if we're talking about like percent increase or percent decrease. And that is the form A, still using that A. And as a B, instead of B, we use 1 plus R. And notice here, instead of an X, I have a T, because a lot of times we use time in our real world phenomena, okay? So A here is still that initial or starting value. That doesn't change. The R is the growth rate per time period. So for that COVID example, that would be the growth rate, or how quickly it was growing per day. If we're thinking about the value of your savings account, if you have a percent interest per year, that would be the growth rate per year, where the time period would be the year. And then T is representing that time period. Now, as we're looking at either of these formats, either the f of x equals a times b to the x, or f of t equals a times 1 plus r to the t power, we can ask kind of three. We're gonna ask and answer three questions from the equation itself. So the first question is going to be, when we look at an equation, is this an example of exponential growth or decay? The second question we can then ask, once we know if it's growth or decay, is what is the growth or decay rate? And then finally, one other thing that's going to be important for us that we can get right from the equation is, what is that initial or starting value? Let's take a look at a few examples where we're going to break apart these equations and answer these three questions. So looking at our first equation here, we have f of x equals 107 times 1.43 to the x power. So the first question, is this growth or decay? Well, to know that, I'm going to look here at this 1.43. That was my base. And this is greater than 1. So if that number there is greater than 1, that is going to be exponential growth. So this is an example of exponential growth because 1.43 is greater than 1. Now, the second question here is asking, what is the growth or decay rate? So I'm going to use, as we're looking at this, I'm going to use this guy right here, the 1 plus r, to figure out, well, what is that growth rate? So we can set up a quick little equation. right? So R is the growth rate, and I know that 1 plus R in this case equals 1.4, excuse me, 3. So if I subtract that 1 from both sides, that's going to give me that R equals 0.43, or as a percent, we're going to multiply by 100 to get 43%. So the growth rate, since it was exponential growth, is 0.43 or 43%. And then finally here, this is asking me what is the initial value. So when I'm looking at the initial value, that's coming from the number that does not have the exponent on it. In this case, that is the 107. So the initial value, A, is 107 in this case. Let's take a look at our second example here. So we have f of x equals 17 times 0.62 to the x power. So looking here, I'm noticing that I have this base of 0.62. 0.62 is less than 1. So this would be a decay function. So exponential decay, because 0.62 is less than 1. To figure out what that decay rate is, we're still going to use that 1 plus R, and we're going to say, oh, that's 0.62. Subtracting the 1 from both sides, that's going to give me an R of 0.38, which if I turn that back into its decimal, or sorry, not decimal, into its percent by multiplying by 100, would be a 38% decay rate. So the decay rate here is 0.38 or 38%. And then my initial value, that starting value, that's coming from here. That's 17. So A, our initial value, is 17. We have one more example before we move, before you're able to move on in your mastery pathway. One more example here. We have f of x equals 3.5 times 2.43 to the t power. Oh, that was a mistake by my part. This over here, since I have a t in the function, it should be a t in my function notation. So if you can just take a moment to change that f of x to f of t, that would be lovely. So now here, what do you think? Is this growth or is it decay? Pause for a moment, see what you think. If you said growth, you would be correct. This is exponential growth. But why? Why is it exponential growth? If you're saying, oh, it's exponential growth because that 2.43, what I'm multiplying by, is greater, or what has the exponent on it, the base is greater than 1, you would be correct. Now take a moment, knowing that this is our base, 2.43, to try to figure out what the growth rate is. So you can pause the video, try to figure out what that growth rate is, and then come back and we'll go through it. So using that 1 plus R, again, we know that that is going to give us 2.43. Same thing we did before. If I subtract 1 from both sides, that's going to give me a rate of 1.43. Turning that into its percent, multiplying by 100, would give me 143%. So the growth rate is 1.43 or 143%. Finally here, what is our initial value, that starting value? circle it in the equation. What do you think it is? If you said it was 3.5, you would be correct. At this time, make sure you've got all of the notes and all of the examples filled out. Go ahead and glue this into your notebooks. And then you can move to the next assignment under modules after the video and notes. Make sure you don't skip any assignments because they will all be graded for you.